In the past, I have produced quite a few videos about the radiation in space on a journey to the moon. These videos have been in constant revision due to new data emerging, corrections that need to be made, and of course, various back and forths between various opponents on this subject. In the beginning, Dr. James Van Allen had first detected glimpses of the Van Allen radiation belts when in 1952 and 1953 he sent raccoons up into space over Greenland. A raccoon is a weather balloon with a rocket attached, in this case with a Geiger counter installed. When the balloon reached its peak altitude, the rocket would fire the rest of the way up into space. From altitudes of nearly 50 kilometers, the Geiger counters would become continuously busy detecting X-rays from electrons hitting the instrument package. Van Allen's fears worsened when his Geiger counters were carried aboard the Explorer 1 and 3 satellites. From low altitudes, the counts per second were low, but when the satellites approached altitudes as high as 1,000 kilometers, the counts per second would rapidly ascend to more than 1,000 times their theoretical expectations, and then they would suddenly just drop to zero. The conclusion was that there was too much radiation for the Geiger counters to cope with.
American Trust Company, for the 10th year on television, proudly brings you Science in Action.
This is a Geiger counter designed on the same principle as that used by Dr. Van Allen in the Explorer flight. As we go on up to 2,000 miles, we have here with us Joe Hilson from the effects group at Livermore, who will put in the cobalt-60 source, which will serve as a source of radiation for the experiment.
That goes right at the top of the...
That's right in the middle of the belt. You'll notice the counter went up here as he stuck that source in.
Yes.
Now, I will turn on the sound here, and we'll imagine that the Explorer is mounted in, that the counter is mounted in the Explorer satellite, and you can hear the counts here, you can hear the sound, and you can also notice the reading on the meter. Now I'll start the takeoff here, and you can see the radiation mount as the satellite goes to higher altitudes, and you'll notice it gets pretty high here. It goes up just as we would expect as it gets closer to the radiation source.
This is the same thing that happened in Dr. Van Allen's experiment.
Exactly. And now we'll jump above 600 miles, and we'll see what happens when we get closer to the source of radiation.
Uh-oh, there it goes back down to zero again.
Yes. The explanation for this is that the satellite had gotten into an area of radiation so strong that the counters were completely jammed. Now we'll return the satellite back down to the lower level, away from the radiation.
In other words, it went back to zero and then came back up again.
That's right, and you can see it's still very high there, Earl. Now we'll go on down to the lower altitude yet. And you can see the counter is now working normally, just as if nothing is wrong.
Well, then it was a question of equipment which was designed to be very, very sensitive, but couldn't take the amount of radiation which was in this area way up above the surface of the Earth.
Exactly, Earl. Dr. Van Allen had run into an area of radiation far stronger than he had expected, and his counters just weren't designed to detect such strong radiation.
After subsequent surveys, with the Geiger counters shielded by a millimeter of lead, starting with Explorer 4 and through to the Pioneer program, Van Allen wrote 2 articles warning people of the lethal radiation he had detected. The first article, published in the March 1959 issue of Scientific American, was titled Radiation Belts Around the Earth, in which he stated,
"Instruments borne aloft by artificial satellites and lunar probes indicate that our planet is encircled by 2 zones of high-energy particles, against which space travelers will have to be shielded. The discovery is of course troubling to astronauts. Somehow the human body will have to be shielded from this radiation, even on a rapid transit through the region."
The second article, published in the December 1961 issue of Space World and titled The Danger Zone, concluded with this blunt statement.
A living organism cannot survive this level of radiation damage. Hence, all manned spaceflight attempts must steer clear of these 2 belts of radiation until adequate means of safeguarding the astronauts has been developed.
Subsequent to the Apollo missions, Van Allen reportedly recanted on his stance about deadly radiation, and his subsequent retraction has frequently been flogged by propagandists. In particular, they are fond of citing this alleged email from Dr. Van Allen.
Dear Mr. Lambert, in reply to your email, I send you the following copy of a response that I wrote to another inquiry about 2 months ago. The radiation belts of the Earth do indeed pose important constraints on the safety of human spaceflight. The very energetic, tens to hundreds of MeV, protons in the inner radiation belt are the most dangerous and most difficult to shield against. Specifically, prolonged flights, i.e. ones of many months' duration, of humans or other animals in orbits about the Earth must be conducted at altitudes less than about 250 miles in order to avoid significant radiation exposure. A person in the cabin of a space shuttle in a circular equatorial orbit in the most intense region of the inner radiation belt, at an altitude of about 1,000 miles, would be subjected to a fatal dosage of radiation in about 1 week. However, the outbound and inbound trajectories of the Apollo spacecraft cut through the outer portions of the inner belt, and because of their high speed, spent only about 15 minutes in traversing the region and less than 2 hours in traversing the much less penetrating radiation in the outer radiation belt. The resulting radiation exposure for the round trip was less than 1% of a fatal dosage, a very minor risk among the far greater other risks of such flights. I made such estimates in the early 1960s, and so informed NASA engineers who were planning the Apollo flights. These estimates are still reliable. The recent Fox TV show, which I saw, is an ingenious and entertaining assemblage of nonsense. The claim that radiation exposure during the Apollo missions would have been fatal to the astronauts is only one example of such nonsense. James A. Van Allen.
Assuming that this email is indeed from Van Allen, nowhere in it does he offer reconciliation for his previous statements about the radiation belts being deadly within a short period of time. In fact, he doesn't even mention these past articles. His failure to reconcile makes this message easy for propagandists to manipulate for their own agenda. This is akin to, for example, NASA flogging around MoonFaker's approval to launch the Challenger in cold weather, which they only got after they pressured MoonFaker to change their original no-launch recommendation, and then neglecting to say that their original recommendation was not to launch.
Challenger, go at throttle up. Challenger, go at throttle up. Flight controllers here looking very carefully at the situation. Obviously a major malfunction.
Van Allen died in August 2006, coincidentally around the same time that the unfiltered Apollo moonwalk videos went missing, so only he can know his true stance on Apollo. We can argue back and forth about Van Allen's stance on radiation until the end of time, but really, all one needs to prove one's case is basic mathematics. You just have to know the trajectory that the Apollo missions allegedly took, the energy level of the particles that they would have encountered, the fluxes of the said particles, and the amount of time they would have been exposed to these particles. Amazingly, all those elements have been provided by perhaps the most unlikely source. In November 2009, Robert Braenig published an article on his website in which he attempted to explain how the Apollo 11 astronauts avoided the radiation belt. After quite a lengthy evaluation of the purported mission flight data, Braenig plots the trajectory over this map of the Van Allen belts. The purple line itself is Apollo 11's supposed trajectory, and the red dots represent 10-minute intervals. The chart itself maps out the fluxes of electrons with energies greater than 0.5 MeV. As you can see from this map, the Apollo 11 crew allegedly spent about 40 minutes within the outer region where the electron flux is 1 million particles per square centimeter per second, and 20 minutes in the most intense region of the outer belt with 2 million particles per square centimeter per second. Now in this discussion, we'll focus only on the outer Van Allen belt since the astronauts allegedly spent more time in there than the inner belt. I'm actually quite surprised that Braenig even used this graph. Instead of using these numbers to calculate the dose rates, Braenig instead overlays his trajectory on a different graph which laughably downplays the dose rates into the millirad range. How about we use these numbers from the earlier graph and see if these millirad numbers are indeed substantiated. Now, we know the fluxes of the Van Allen electrons with energies greater than 0.5 MeV, but just how high is greater than 0.5 MeV? Well, according to the Wikipedia article on the Van Allen belts, the outer belt consists of electrons with energies ranging between 0.1 MeV and 10 MeV. I've seen much higher energies for electrons mentioned in other places, but we'll focus on electrons with energies between 1 MeV and 10 MeV. Now, attenuating electrons with 1 million electron volts of energy requires a shield rated at 0.545 grams per square centimeter. However, a general rule of thumb is the higher the energy level, the further the electrons will penetrate. So 10 MeV electrons would require a shield rated at 5.45 grams per square centimeter. And even if you had that shielding, you would still require an inner layer of high-Z material to attenuate the bremsstrahlung. That is, the energy that the electrons lose in the form of X-rays when stopped in matter. NASA claims that the Apollo Commander Module was rated at 7 to 8 grams per square centimeter. If true, this would stop all electrons with energies up to 14.7 mega-electron volts. But, as shown in my previous video, this 7 to 8 grams per square centimeter rating applies only to the heat shield, with the rest of the ship being rated at about 3 grams per square centimeter.
Another thing that needs pointing out is that this 7 to 8 grams per square centimeter figure refers to the hull, not the entire capsule. The CM was a conical pressure vessel with a maximum diameter of 3.9 meters at its base and a height of 3.65 meters. It was made of an aluminium honeycomb sandwich bonded between sheet aluminium alloy. The base of the CM consisted of a heat shield made of brazed stainless steel honeycomb filled with a phenolic epoxy resin as an ablative material and varied in thickness from 1.8 to 6.9 centimeters. Essentially, the thick hulls functioned as a heat shield and was made from materials designed to burn away on re-entry. The CM walls were a thin aluminium honeycomb bonded together between aluminium sheets. These sheets were around 2 millimeters each, and the honeycomb added another millimeter at most, bringing the total aluminium thickness to 5 millimeters. Multiplying this thickness by the aluminium's density gives us an aerial density of 1.35 grams per square centimeter for the CM walls. A good deal less than the 7 to 8 he cites, wouldn't you say? And then, as a last resort, the Vandal goes on to claim that the ablative phenolic resin also acted as a radiation shield. Phenolic resin has a density of 1.1 grams per cubic centimeter, which is comparable to water. Doing the math indicates that the aft heat shield, at its thickest point, had an aerial density comparable to the 7 to 8 grams per square centimeter he cites. But, if we apply that same math to the ablative covering the rest of the hull, we find it only has an aerial density of about 2 grams per square centimeter.
This would only attenuate electrons with energies up to 6.1 mega-electron volts, and again, even if the entire craft was rated at 8 grams per square centimeter, it would still need an inner layer of high-Z material to block out the X-rays. So let's look at the highest primary dose from 10 MeV electrons alone. First, we convert the flux into the number of electrons per square meter per hour, and we get 36 trillion electrons per square meter per hour. Next, we multiply that by the front surface area of an astronaut, and we find he would have been hit by 30.6 trillion of those electrons every hour. Multiply that by the energy of each electron, and we find he's absorbed 306 quintillion electron volts every hour. Now let's see, 1 mega electron volt is equal to 1.6 by 10 to the minus 13 joules. So that means he's absorbed about 49 joules per hour. Now here's where the gloves go off. We divide that by the body mass of an adult, which averages 75 kilograms, and we get about 0.65 gray per hour. 1 gray equals 100 rad. So we multiply that by 100 and we get 65 rad per hour. That's the primary dose from the less intense regions. If we apply those same calculations for the region with double the flux, we get 130 rads per hour. For the sake of thoroughness, if we apply those calculations again for electrons with energies of, say, 7 MeV, we get about 46 rads per hour for the less intense region and 91 rads per hour for the most intense region. All that is left is to multiply these dose rates by the time allegedly spent in these two regions. Looking back to Brannig's graph, we see that the Apollo 11 capsule allegedly spent 40 minutes in the less intense region and 20 minutes in the most intense region. So for the 7 MeV electrons, Multiply the 46 rad per hour dose rate by the 2/3 of an hour allegedly spent in there, and we get about 30.5 rads. For the most intense region, we multiply the 91 rad per hour dose rate by the 1/3 of an hour allegedly spent in there, and we get about 30.5 rads. Fancy that. Add the two together, and we get about 61 rads. And of course it was a two-way trip, so the end dose ends up being 122 rads. For the doses with 10 MeV electrons, we get 87 rads for just one trip, and 174 rads for the two-way trip. I took an average of the two, and got 148 rads for the two-way trip, or 74 rads for just one trip. 70 rads is enough to cause symptoms like headaches, low blood counts, and temporary sterilization in males, while anything over 100 rad is enough to cause vomiting, nausea, fatigue, and a significant drop in the immune system. But I'm afraid it only gets worse than that, because so far I have only assumed that the electron energy peak was 10 MeV. As I said before, I have seen much higher energies for electrons in the outer Van Allen belt mentioned in other places. This NASA site, for example, tells us that electrons in this outer belt carry between 10 to 100 million volts of energy on average. I assume by volts they mean electron volts. A volt is a unit of electric potential, not energy. Anyways, the average of 10 and 100 megaelectron volts is 55 megaelectron volts. Stopping these would require a shield rated at about 30 grams per square centimeter, which is about 4 times the aerial density of the Apollo Commander module at its thickest point. So yes, these would by all means go right through the spacecraft. If we redo the calculations for the average energy of 55 megaelectron volts, then we find the primary dose is 360 rads per hour for the less intense region, and over 718 rads per hour for the most intense region. This gives us 480 rads for just one trip through the Van Allen belt. Just one trip. 480 rads. And remember, 500 rads is enough to kill you. Now, assuming that the electrons have been attenuated, we should also calculate the bremsstrahlung. The authors of Astronomical Engineering and Science explain that the fraction of energy given up as bremsstrahlung will be given by the formula F equals kZe, where K is 7 by 10 to the minus 4 per megaelectron volt, Z is the atomic number of the material attenuating the electrons, and E is the original energy of the electrons. Now, aluminium has an atomic number of 13. For 55 MeV electrons, we cancel the units and we are left with a fraction, 0.5005. This fraction needs to be multiplied by the original energy of the electrons. This gives us 27.53 megaelectron volts. This puts them in the category of what are called hard X-rays, which can penetrate solid objects, such as people. Even if we assumed that the electrons at energies of 1 megaelectron volts, their bremsstrahlung would still fall in the hard X-ray range. So just how much energy are we talking about here? Well, for 55 MeV electrons, which thus produce X-rays with 27.53 megaelectron volts of energy, that gives us 4.4 by 10 to the minus 12 joules. Now, hold on to that number because the next two steps depend on which region they are travelling through. In the less intense region, we are looking at 30.6 trillion X-rays per hour, and in the most intense region, double that. Multiply those hourly hit rates by the energy that we found earlier, then divide that by the body mass of an adult to convert to grays, then convert to rads, and we get about 180 rads per hour for the less intense region, and 360 rads per hour for the most intense region. And so this gives us 240 rads for just one trip through the Van Allen belts, and 480 rads for two trips. This means that the secondary dose for two trips through the belt is almost exactly the same as the primary dose for just one trip. And this secondary dose assumes that all electrons with energies up to 100 MeV have been attenuated. At best, 8 grams per square centimeter will stop all electrons with energies up to only 14.7 MeV, well below the average energy of the outer Van Allen belt. And remember, 500 rad is enough to kill you. Death by electrons, anyone? One small step for man and one giant leap for mankind? I think not.